We're going to talk about one final topic with probability today, and that is counting. Now, you might wonder why counting fits into this probability chapter. And the answer for that is when we're finding probabilities, we've been counting the number of favorable outcomes or the outcome we're interested in and dividing it by the total number of possibilities. So we've been counting this whole time, except we've been limiting ourselves to things that are easier to count. So now we're going to open the gates to allow us to count things that are a little bit more complicated. Now, this section is going to have more formulas than we've had in the previous sections. However, there's really only two big idea things happening, even though we're going to look at 5 different methods for counting the number of possible outcomes. So keep that in mind. I'm going to be linking all of these things back to each other along the way as well. Try not to get too overwhelmed, all right? So the first one and the big one that I really want you to focus on is this idea of the multiplication counting rule. So for a sequence of events in which the first event can occur n sub 1 ways, second event can occur n sub 2 ways, third event n sub 3 ways, so on and so forth, then the total number of outcomes is going to be found by multiplying n sub 1 times n sub 2 times n sub 3 and so on. All of those n values multiplied together is going to give us our total number of outcomes. All right, that's the multiplication rule. So let's take a look at an example of this. So say you have a password that's 4 digits long, and any digit can be any of the digits 0 through 9. So all 4 digits have the options of 0 through 9. If you were trying to guess the passcode, or there was a hacker trying to guess your passcode, then what's the probability of guessing the password on the first attempt, the correct passcode? So to know this, we know that there's one correct passcode, so we have the numerator of our probability taken care of. However, we need to know how many total possible passwords there are. And this is a little bit more complicated than what we've seen in the past. So we're going to go to our multiplication rule. Notice that there are 10 different possibilities for each digit with the numbers 0 through 9. That's 10 possibilities. So the total number of different possible passcodes is going to be n1 times n2 times n3 times n4, and each of those is going to be 10 since there's 10 possible digits. So we'll get 10 times 10 times 10 times 10, or 10,000 different possible passcodes. Since each of these is equally likely, then the probability of getting the correct passcode on the first attempt is 1 in 10,000, or 0.0001. Our second rule is just a version of the multiplication rule. Right? It's called the factorial rule. It's the number of different arrangements, when order matters, of n different items when all n of them are selected. And we use this exclamation point notation. So we write it as n with an exclamation point, and we read it n factorial. So that notation, that exclamation point, what does it tell us to do? What it tells us to do is to multiply by every number from n down to 1. There's also this special definition that 0 factorial is equal to 1. But if I wanted to know, say, 2 factorial, I would do 2 times 1. 3 factorial is 3 times 2 times 1, and so on. All right. So the factorial rule is based on this idea that you have n different ways to select the first item, and then since you've chosen that one and you can't use it again because we have to use all n, there are n minus 1 ways to choose the second item. And then since we can't use either of those two as the third item, then there's n minus 2 different ways to choose the third item, and so on until we're down to the last item, when there's just one way to choose that item. So it really is just the multiplication rule where the numbers are decreasing each time by 1. And we get to use this exclamation point as a factorial to save us from having to write 10 times 9 times 8 times 7 times 6 or something like that all the way down, right? So let's take a look at an example of this. So a statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harrison, Pew, and Zogby polling companies. So how many different travel itineraries are possible? Well, you're not going to go to each of them and then could go to the same ones again. You're going to go to one of them, and then you have to go to a different one, and then to a different one. So this is not the multiplication rule the way we saw it in its first iteration. This is the factorial version of it. All right. So then we want to know if the itinerary is randomly selected, what's the probability that the presidents are visited in order from youngest to oldest? So let's first talk about how many possible itineraries we have. Well, there's 5 different presidents. So that means the first president we visit, there's 5 ways to do that. Then once we've visited that president, there's 4 remaining presidents to visit. And then there's 3 remaining, and then 2, and then 1. So using the multiplication rule, we would know that we need to multiply 5 times 4 times 3 times 2 times 1. Factorial rule comes along and says, you know what? You don't have to write out 5 times 4 times 3 times 2 times 1. You can instead use this exclamation point and write it as 5 factorial. So if we do that, we get 120. All right. Also, your calculator has a factorial button, so you don't even have to hit 5 times 4 times 3 times 2 times 1 into your calculator either. You can just hit 5 factorial and it will give you 120 as an answer. All right. So then we want to know the probability that we visit in order of age. Well, there's only one way to do that, and there were 120 possible itineraries. They're equally likely, so our probability is 1 out of 120. All right. Permutations and combinations. These are 2 different rules, and again, are just kind of modifications of that multiplication rule, with our second big idea coming into play as well. So permutations are just items being arranged and the order matters. All right, so if I'm taking the letters A, B, and C, there are 6 possible ways to arrange the letters A, B, and C. They're all listed there. Those are permutations of the letters A, B, and C. Right. This other concept, combinations, which is where our new idea is going to come into play too. Combinations are items that the order doesn't matter in. So we would count ABC, BAC, CAB, and so on. All 6 of those arrangements that were all different permutations of the letters A, B, and C, they're all a single combination. So if you need something to help you remember that position matters, permutations, positions, PP, we've got that mnemonic, and combinations are like forming committees. People on the committees all have the same position. They're all a committee member. So combinations, committees. All right. Order doesn't matter. All right. So our permutations rule. This has division in it, but it's really just our multiplication rule again. All right. So we have n different items available, and we're going to select R of them where the order matters. What we're going to do is we're going to be choosing R things, and the first thing that we choose, we're going to choose something where there's n options. The second thing we choose will have n minus 1 options, and so on. This sounds like that factorial rule, right? Which is why n factorial's in our numerator. And having n minus r factorial in the denominator, all that's doing is cutting off all but r of the numbers that we're multiplying times each other, because we only need to fill r positions. So again, this could be done using the multiplication rule, just as easily as this rule most of the time, or at least the intuition for it all of the time. Multiplication rule is something you need to be thinking back to. All right. So let's take a look at an example of this playing out. So in a horse race, a trifecta bet is won by correctly selecting the horses that finished first, second, and third, and you must select them in the correct order. So looking at the 140th running of the Kentucky Derby, there were a field of 19 horses. So we want to know how many different trifecta bets are possible, and if a bettor randomly selects 3 of those horses for a trifecta bet, what is the probability of winning by selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third, as they did? So what's the odds of winning this trifecta bet? Do all the different possible trifecta bets have the same chance of winning? And we can ignore these dead heats for when they win, or for when they tie, sorry. All right, so solutions. First off, we're looking for how many trifecta bets do we have? All right, so N is 19. There's 19 horses available, and we need to choose 3 of them. So we want to multiply 19 times 18 times 17. The multiplication rule and our factorial rule, we've got that intuition. We know that's what we need to do. And in fact, if you multiply those 3 numbers together, you're going to get 5,814. Now, what's happening with our permutation rule here is we have 19 factorial, which is starting out with 19 times 18 times 17 times 16 and so on. And in our denominator, we have 19 minus 3 factorial. 19 minus 3 is 16 factorial. So what's happening is we're dividing by 16 and 15 and 14. So every number after 17 is getting canceled out in that multiplication and division. So we really are left with 19 times 17 times 18 times 17, which is what our intuition in the multiplication rule told us it should be. The benefit of this is if we were choosing more than 3 of them, then we would be able to use our calculator to help us out, and it would be more efficient with our calculator. As it is, it might not be more efficient with your calculator to type this in than to type in 19 times 18 times 17. But again, both ideas, they're going to get you to the same place. So now let's talk about this probability aspect of it. All right, so there's 5,814 different possible arrangements of 3 horses selected from the field of 19. So if one of these arrangements is randomly selected, there's a probability of 1 out of 5,814 that the winning arrangement is selected. All right, so again, there's this 5,814, but we were also asked, are they equally likely? But they don't actually have the same chance of winning because some of the horses tend to be faster than others. That's why we get these odds when we bet, or when we look at betting. So we are given odds, and that's telling us that some horses are more likely to win than others, which makes the winning bets or the different trifectas have different payoff rates. They'll pay different amounts depending on how likely the horses are to actually win, the 3 that are selected. So as it turned out in that example, a winning $2 trifecta bet won $3,424.60. All right. So now we're going to tweak the permutation rule just a little bit. So we chose the permutation rule, or we were talking about the permutation rule when we were selecting these things, all of them without replacement, and order mattered. And we could distinguish between items. If 2 items are alike, say I'm taking the letters in the word banana and I'm wondering how many different ways can I arrange those letters. Well, the A's are interchangeable and the N's are interchangeable, but the B's from the A's from the N's, they're not interchangeable. So that's where this rule comes into place. All right, so we have N objects, we're choosing all of them, and we want to know how many orders we can put them in. However, we can't tell the difference between some of them. All right, so if we have n sub 1 of them are alike, so in banana there are 3 A's, so that's 3 alike, and then there's 2 N's, right? Yeah, all right, so 2 N's, then we have 2 alike also, so we have 3 alike and 2 alike. Then we're going to divide out by 3 factorial and 2 factorial, and that is dividing by the different orders that the A's may fall in and the different orders that the N's may fall in that we can't tell the difference. All right, so this is telling us, again, how many orders do we have of all n objects when we can't tell the difference between some subsets of those n objects. So let's take a look at an example here. So we have a survey. We're going to take a look at the way pollsters design surveys. So sometimes they repeat questions just to see if you're thoughtlessly providing answers to just finish quickly. It's a big problem in survey research, actually. All right, so in one particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. All right, it's a lot to be identical to each other for a 10-question survey. So for the survey, how many different arrangements are possible? Okay, and then also, is it practical to survey enough subjects so that every different possible arrangement is used? It's a practicality question that we'll talk about real briefly. So the number of different possible surveys. 10 questions, we're going to use all of them. So 10 factorial is our numerator. And if we could tell the difference between every question, we would be done with 10 factorial. However, 2 of them are identical, so I can't tell if I ask those questions this way around or this way around. So I divide out by those 2 different arrangements, which happens to be 2 factorial. And then 3 of them are identical. So I have 1, 2, and 3, and I don't know if they're asked in the order 1, 2, and 3, 3, 2, and 1, 2, 3, and 1, 2, 1, and 3. Any of those possible orders, I can't tell the difference because they're identical questions. So those 3 questions can be put into any of 6 orders, all of which are identical to me. So I divide out by that 6, which we can find by saying it's 3 factorial. So we're going to divide out by 2 factorial times 3 factorial, or 2 times 6. And when we do that, we find that there are 302,400 ways to survey given 10 questions where 2 of them are identical and then another 3 are also identical. So the practicality of this, is it possible to use them all? Sure. But the chances that you conduct a survey with 302,400 participants, very unlikely. Most surveys have a number of respondents closer to the 1,000 range, though it really depends on the survey. So it's kind of a little bit weird to give a ballpark here even. All right, our 5th and final rule, combinations. Combinations is just kind of that permutations idea, with the idea that we're not going to choose them all and we can't tell the difference. All right, so again, our 4th rule and 3rd rule merging together, and yet another time that we're basically doing the multiplication rule with one added little tweak. So for our combinations rule, we're going to be taking n factorial divided by n minus r factorial. What that does is it takes r objects, that's our permutation rule. Notice n factorial divided by n minus r factorial. So that's how we take r items from n different items when the order matters. Except the order doesn't matter of all r items. So when the order didn't matter, or those items were indistinguishable to us, we had to divide out by how many of them there were that were indistinguishable factorial. And so in doing that, what we have is n divided by n minus r factorial, and then we're also dividing out by r factorial to divide out by the orders that they can fall into. So let's take a look at an example of this. The lottery. All right. California's Fantasy 5 lottery game. Winning jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The order does not matter that they're drawn in. So our first question is, how many different lottery tickets are possible? And then finally, find the probability of winning the jackpot when one ticket is purchased. Our combinations rule. All right. So 39 different numbers available, and we must select 5 of them. So 39 available, we're selecting 5, so we would do 39 times 38 times 37 times 36 times 35. Well, we get that by doing our 39 factorial divided by 34 factorial. But then the order of the 5 numbers doesn't matter. They're indistinguishable in this idea, all right? Even though we can tell the difference, we treat them as indistinguishable because we don't care what order they show up in. So we divide by the 5 factorial orders that they can fall into. So what that leaves us with is 39 factorial divided by 34 factorial times 5 factorial. That's following our combinations rule, but it's also following the intuition that the multiplication rule and our permutation rule and this idea of like things being able to be distinguished versus not gave us, all right? So don't get so hung up in the formula that you lose the intuition. The intuition will get you there, all right? So 575,757 ways that we can choose 5 of these 39 numbers when we don't care about the order. So for part B, we're looking at the probability of winning if we buy just a single ticket. Well, that's 1 out of 575,757, right? So this probability, you're very unlikely to win the lottery if you buy a single ticket, right? So yeah, that's the idea here. So again, focus on multiplication rule, all right? And remember that dividing out by however many orders things can show up in when you can't distinguish between them or when you don't care that you can distinguish between them, those 2 big ideas will get you all 5 of these rules every time.